Good evening, and welcome to the Late Lab. I'm very glad you found your way here tonight. Tonight we're looking at something most of us have played with since childhood, yet which becomes surprisingly strange the moment we ask what it actually is. A magnet can pull on another object from across empty space. It can push another magnet away without touching it, and somehow a small piece of metal can keep doing this day after day without batteries, fuel, or any obvious moving parts, which is perhaps a slightly inconvenient thing to think about just before trying to fall asleep. Before we get into it, I'd love to know where you're listening from tonight. Maybe you're already tucked into bed, stretched out on the sofa, or travelling home beneath the glow of passing streetlights. Wherever you are, make yourself at home, and please feel free to leave a comment and let me know. I try to read every single one, and it genuinely means a great deal to know who's out there in the dark with me. And if you'd like more nights like this one, subscribing means you'll always find your way back here. If you're already part of the channel, thank you for coming back. So, dim the lights, and let's begin. What is magnetism actually made of? And what is really happening in the invisible space between two magnets? There is something quietly strange about holding two magnets in your hands. Bring opposite poles toward one another, and they seem almost eager to meet. You can feel the pull growing stronger before the magnets ever touch. Turn one around, and the experience changes completely. Now they resist. Push them closer, and the invisible opposition becomes surprisingly firm, as though something unseen has filled the gap between them. And yet, when you look into that gap, there appears to be nothing there. No thread connects the magnets. No visible substance flows between them. There are no tiny mechanical arms reaching across the empty space. Nevertheless, one object knows, in a very physical sense, that the other is nearby. That simple observation contains much of the mystery of magnetism. For much of human history, magnetism seemed almost magical because it allowed objects to influence one another without obvious contact. Modern physics gives us a far more precise description, although perhaps not one that makes the phenomenon feel any less remarkable. Magnetism is not a material fluid stored inside a magnet. It is not a substance slowly leaking into the surrounding air. Instead, magnetic effects arise from the electromagnetic field and from the behaviour of electrically charged matter. That electromagnetic field exists throughout space. Electric charges interact with it, moving charges can generate magnetic effects, and the quantum properties of particles such as electrons become essential when we want to understand why certain pieces of matter can become permanent magnets. We encounter these effects constantly. A compass needle rotates until it approximately aligns with Earth's magnetic field. Two bar magnets can attract or repel. Inside an electric motor, magnetic forces act on current-carrying conductors and help turn electrical energy into rotation. Sprinkle iron filings around a magnet, and the filings arrange themselves into elegant patterns that reveal the direction of the surrounding magnetic influence. The filings are not showing us literal threads hidden in space. They are responding to what physicists call a magnetic field. A field is a way of describing how a physical influence exists throughout a region of space. At every location around a magnet, the magnetic field has a particular strength and direction. Place something capable of responding to magnetism at that position, and the field helps determine what will happen to it. This distinction matters. The magnet is the piece of matter sitting on the table. The magnetic field is the physical field extending through the region around it. Moving farther away usually makes the magnetic influence weaker, but it does not suddenly disappear at some sharp boundary. Earth itself provides a familiar example. A small compass can respond to Earth's magnetic field even though the source of that field lies thousands of kilometers beneath our feet. Not everything responds to magnetic fields in the same way. Iron is famous for its strong magnetic behaviour. Cobalt and nickel can also form strongly magnetic materials. A piece of copper behaves very differently. Aluminium behaves differently again. Glass and water may seem almost completely indifferent to an ordinary fridge magnet. Strictly speaking, nearly all matter responds to magnetic fields in some way, but the strength and nature of that response can vary enormously. In everyday life, those differences are so large that we casually call some materials magnetic and others non-magnetic. Humans have been trying to understand these differences for a very long time. One of the major early figures was the English physician and natural philosopher William Gilbert. In 1600, Gilbert published a remarkable work called De Magneti, based on extensive experiments with lodestones, compasses, and magnetized materials. Gilbert rejected many of the superstitions that had accumulated around magnetism and tried to investigate the subject systematically. One of his most important conclusions was that Earth itself behaves approximately like a great magnet. He even experimented with a spherical piece of magnetic material, sometimes called a terrella, meaning little Earth, and studied how compass needles behaved around it. That was a major conceptual step. The compass was not being mysteriously pulled towards some special point in the distant north. It was responding to the magnetic environment created by the planet itself. But even if we accept the existence of a magnetic field, another question immediately appears. Where does that field come from? An electromagnet offers one relatively intuitive answer. Send electric current through a coil of wire, and the moving electric charges generate a magnetic field. Switch off the current, and the field largely disappears. A permanent magnet is stranger. A good permanent magnet can remain magnetized for years. It does not have a battery hidden inside it. There is no obvious macroscopic current circulating through the material. It does not need to be plugged into a wall each evening to recharge its magnetism. So what inside that piece of matter keeps the magnetic field there? The answer eventually takes us into the atom. Electrons possess electric charge. Their quantum states can carry orbital magnetic effects, and electrons also possess an intrinsic property called spin, which gives them an intrinsic magnetic moment. Inside certain materials, interactions between enormous numbers of electrons can cause these tiny magnetic moments to organize collectively. That organization is one of the central reasons a piece of iron can become a magnet, while a piece of glass normally cannot. And beneath even that description lies a deeper one. Electricity and magnetism are not ultimately separate forces. They are interconnected aspects of electromagnetism. In modern quantum physics, electromagnetic interactions are described through a quantum field, with charged particles such as electrons interacting with that field. So the invisible push between two magnets is not produced by some mysterious magnetic substance hiding inside the metal. It is the visible consequence of something much deeper, electrically charged quantum matter interacting through the electromagnetic field. A force that feels almost like magic in your fingertips begins, beneath the surface, with fields, electrons, motion, and some of the strangest properties allowed by quantum mechanics. For centuries, magnets seemed to belong to their own peculiar corner of nature. A lodestone could pull on iron, a compass needle could turn toward the north. Two magnets could attract or repel one another across empty space. Electricity, meanwhile, seemed like something rather different. It could build up as static charge, leap as a spark, or travel through a conducting material. Then, in the early 19th century, one simple experiment began to show that these were not separate phenomena after all. The crucial observation came from the Danish physicist Hans Christian Ørsted in 1820. Ørsted had been interested in the possible connection between electricity and magnetism for some time. During an experiment involving an electric circuit, he noticed that a compass needle positioned near a wire moved when current passed through that wire. The result was subtle, but its implications were enormous. A compass needle responds to magnetic influences. If an electric current caused the needle to turn, then electricity was somehow producing magnetism. More precisely, electric charge moving through the wire was creating a magnetic field in the surrounding space. That was an extraordinary shift in perspective. The electrical current was not merely doing something inside the metal conductor. Its influence extended outward into the region around the wire, where it could act on a completely separate magnetic object. The geometry of this magnetic field was also unusual. Around a long, straight current-carrying wire, the magnetic field forms closed circular paths centered on the wire. If the direction of the current is reversed, the direction of the magnetic field reverses as well. The field does not simply point outward from the wire in the way an electric field can point away from a positive charge. Instead, it curls around the current. This relationship between electricity and magnetism was quickly investigated in greater detail by the French physicist André-Marie Ampère. Ampère studied the forces acting between wires carrying electric currents. He found that two long parallel wires carrying currents in the same direction attract one another. If the currents travel in opposite directions, the wires repel. Once again, there was no mechanical connection joining the wires. The currents created magnetic fields, and those fields influenced the other current-carrying conductor. This helped establish an important principle. Electric currents produce magnetic fields, and magnetic fields can exert forces on moving electric charges. The discovery provided one of the first strong hints that electricity and magnetism belonged to a single interconnected system. It also suggested a practical way of creating magnetic fields. Instead of using a naturally magnetic rock or a permanent magnet, one could simply send electric current through a wire. And with a little clever arrangement, the effect could be made much stronger. If a straight wire is bent into a loop, the magnetic fields produced by different sections of the wire reinforce one another near the center. Wind that wire into many loops to form a coil, and the combined effect becomes stronger still. A current-carrying coil produces a field whose large-scale shape resembles the magnetic field of a bar magnet, with one end behaving like a magnetic north pole and the other like a magnetic south pole. Place a suitable piece of iron inside the coil, and the magnetic field can become much stronger. This is the basic idea behind an electromagnet. Unlike a permanent magnet, an electromagnet can be switched on and off. When current flows, a magnetic field is produced. Reduce the current, and the field weakens. Reverse the current, and the magnetic polarity reverses. That simple principle appears in an enormous range of technologies. In an electrical relay, an electromagnet can move a mechanical switch. In a loudspeaker, magnetic forces act on a current-carrying coil attached to a cone, producing vibrations in the air that become sound. Electric motors use magnetic forces to create rotation. Magnetic locks use electromagnets to hold doors securely in place. Industrial scrapyards can use enormous electromagnets to lift heavy pieces of iron and steel, then release them simply by switching off the current. Generators make use of the same relationship from another direction, with changing magnetic environments helping produce electrical currents. By the 19th century, magnetism was no longer something confined to mysterious pieces of naturally magnetic stone. It could be manufactured, controlled, strengthened, weakened, and reversed using electricity. But this success created a new puzzle. An electromagnet makes sense at first glance because we can identify the electric current responsible for its magnetic field. Charges are moving through the wire, and the resulting field can be measured around it. A permanent bar magnet does not seem to work that way. There is no obvious wire running around inside a piece of magnetized iron. No battery is driving a macroscopic current through it. You can leave the magnet sitting quietly on a shelf and its magnetic field remains. So if moving electric charge can create magnetism, where is the equivalent motion inside an ordinary permanent magnet? The answer would eventually require physicists to look far beneath the surface of matter. Inside atoms, electrons carry electric charge. Their quantum states possess magnetic properties, and those magnetic contributions can sometimes organize themselves across enormous numbers of atoms. The discovery made by Hans Christian Ørsted therefore opened a door much deeper than it first appeared. Electricity could create magnetism. And once that connection was established, the next question became unavoidable. Perhaps the magnetism inside ordinary matter was also connected, somehow, to the behaviour of electric charge. The discovery that an electric current could create a magnetic field raised an intriguing possibility. Perhaps electricity and magnetism were not merely related in one direction. Perhaps the connection worked both ways. That possibility became much clearer through the work of Michael Faraday. Faraday was one of the great experimental physicists of the 19th century. He had relatively little formal mathematical education, yet his physical intuition was extraordinary. Rather than thinking of electrical and magnetic forces as mysterious influences somehow reaching instantly across empty space, Faraday began imagining that the space around charges and magnets possessed physical structure. He described what he called lines of force. Today, diagrams of magnetic field lines are so familiar that they can seem almost obvious. Place iron filings around a bar magnet, and the filings arrange themselves into sweeping curves running between the poles. But for Faraday, the deeper idea was important. The lines were not simply decorative marks on a diagram. They represented the way a field occupied the space around an electrical or magnetic source. The region between two magnets was therefore not physically irrelevant just because it looked empty. Something was happening there. Faraday provided an even stronger demonstration of this in 1831 through his discovery of electromagnetic induction. He found that a changing magnetic environment could produce an electric current in a conductor. For example, moving a magnet through a coil of wire can create an electric current in that coil. Holding the magnet perfectly still produces no sustained induced current. Move it again, and the current returns. The crucial ingredient is change. A changing magnetic field produces an electric field, and that electric field can push electrically charged particles through a conducting material. This was a remarkable complement to the discovery made by Hans Christian Ørsted. Electric current could create a magnetic field, and now a changing magnetic field could generate an electric effect. Nature was beginning to look considerably more unified. Faraday developed this picture mainly through physical experiments and geometric intuition. The person who eventually transformed it into a comprehensive mathematical theory was the Scottish physicist James Clerk Maxwell. During the 19th century, Maxwell brought together several previously separate laws describing electricity and magnetism. These included results associated with Charles Augustin de Coulomb, André-Marie Ampère, Michael Faraday, and others. But Maxwell did more than simply collect existing ideas. He recognized that one important piece was missing. Ampere's work had connected electric currents with magnetic fields. Maxwell realized that a changing electric field could also act as a source of magnetic field, even where there was no ordinary conducting current flowing. This addition was profound. It meant that changing electric fields could create magnetic fields, while changing magnetic fields could create electric fields. Imagine an electric field beginning to change. That changing electric field produces a magnetic field. The changing magnetic field can then produce an electric field elsewhere. The disturbance does not have to remain attached to the original source. It can travel. Maxwell's equations therefore predicted the existence of electromagnetic waves. When Maxwell calculated the speed at which these waves should propagate, he found something extraordinary. The predicted speed matched the known speed of light. The conclusion was difficult to avoid. Light itself was an electromagnetic wave. Visible light, which human beings had studied for thousands of years, turned out to belong to the same physical phenomenon as electricity and magnetism. A beam of light travelling through space contains oscillating electric and magnetic fields. The electric component changes continuously. The magnetic component changes with it. Together they propagate through space at approximately 300,000 kilometers per second in a vacuum. Magnetism had suddenly become part of something far larger. The magnetic field around a bar magnet was not one isolated substance. The electric field around a charged object was not another. They were aspects of a single electromagnetic field. This is one of the great unifications in physics. It also changed what physicists meant when they spoke about apparently empty space. A field can exist in a region even if there is no ordinary matter there. Electromagnetic radiation can cross the vacuum between the Sun and Earth. Radio signals can travel through space. Starlight can spend millions or billions of years crossing enormous cosmic distances before eventually reaching a telescope. The space through which these signals travel does not need to contain air, wires, or some invisible mechanical material carrying them along. The electromagnetic field itself can propagate through the vacuum, and fields can carry energy. Sunlight warms your skin because electromagnetic radiation transports energy from the sun. A radio transmitter sends electromagnetic energy outward through space. A charged capacitor stores energy in an electric field. An inductor stores energy associated with a magnetic field. Even the static magnetic field surrounding a permanent magnet is associated with a physically meaningful distribution of field energy. This makes the word field much more than a convenient mathematical label. Fields can influence particles. They can transport momentum. They can contain energy. Their changing configurations can propagate across enormous distances. By the end of Maxwell's work, the question of what magnetism was had therefore changed dramatically. It was no longer enough to imagine that magnets somehow exerted forces across empty space. The magnetic field itself had become part of the physical description of nature, and electricity and magnetism, once treated as separate phenomena, had become two intimately connected aspects of one electromagnetic reality. Once electricity and magnetism had been brought together by Michael Faraday and James Clerk Maxwell, another strange feature of the relationship began to emerge. Whether something looks electric or magnetic can depend partly on how you are moving. To understand why, it helps to begin with the Dutch physicist Hendrik Antoon Lorentz. During the late 19th century, Lorentz helped develop the mathematical description of how electric and magnetic fields act on charged particles. The resulting idea is known as the Lorentz force. An electrically charged particle placed in an electric field can experience a force even if the particle is initially stationary. A magnetic field behaves differently. Its magnetic contribution depends on the motion of the charged particle relative to the field. A stationary electric charge therefore creates an electric field around itself. Once charges are moving, magnetic effects can also appear. This already hints that motion is somehow woven into magnetism. The connection became much deeper in 1905, when Albert Einstein introduced the special theory of relativity. Special relativity is famous for ideas such as time dilation, length contraction, and the fact that the speed of light in a vacuum has the same value for every inertial observer. But it also transformed the way physicists understood electricity and magnetism. Imagine a long wire carrying an electric current. Inside the wire are negatively charged electrons moving through a material that also contains positively charged atomic nuclei. From the point of view of someone standing beside the wire, the positive and negative charges may approximately balance overall, leaving the wire electrically neutral. Yet because the electrons are moving, the wire produces a magnetic field around itself. Now imagine another charged particle moving alongside the wire. From the first observer's perspective, that particle can experience a magnetic force because it is moving through the magnetic field produced by the electric current. But suppose we change perspective. Imagine travelling alongside the moving particle so that, from your point of view, the particle is momentarily at rest. The situation cannot simply stop producing a force, merely because you have changed how you are moving. Physics must remain internally consistent. Special relativity provides the answer. From this new state of motion, the spacing of charges inside the wire can appear different, because distances along the direction of motion are affected by relativistic length contraction. The balance between positive and negative charge densities can therefore change. What looked partly like a magnetic force in one reference frame can appear partly as an electric force in another. No physical force has mysteriously vanished or appeared. The observers are describing the same electromagnetic interaction from different states of motion. This is why people sometimes say that magnetism is electricity viewed through relativity. There is an important truth hidden inside that phrase, but it can also be misleading if taken too literally. Electric and magnetic fields are deeply connected by special relativity. Changing the observer's motion can alter how much of an electromagnetic field is described as electric and how much is described as magnetic. But it does not follow that every magnetic phenomenon can be completely explained by imagining ordinary static electric charges from a clever reference frame. Permanent magnets, for example, depend crucially on quantum properties of electrons. These include intrinsic spin, quantum statistics, and interactions between electrons inside matter. Those ingredients cannot be recreated by classical electrostatics alone. So relativity reveals something profound, but it is not the entire story. The deeper lesson is that electric and magnetic fields are not fundamentally independent objects. In special relativity, they belong to a single structure called the electromagnetic field. Physicists can represent this unified structure mathematically using something called the electromagnetic field tensor. The word tensor may sound as though bedtime has taken an unfortunate turn, but the underlying idea is quite gentle. It is simply a mathematical way of packaging the electric and magnetic components together so that their behaviour remains consistent when observers move differently. One observer may describe a particular electromagnetic situation as containing a certain electric field and a certain magnetic field. Another observer moving relative to the first can measure different values for those two components, but both are describing the same underlying electromagnetic field. This is rather like viewing the same landscape from different angles. The proportions of what appears horizontal and vertical in your view can change, while the landscape itself remains the same. Electricity and magnetism behave in a much more precise mathematical way, of course, but the basic lesson is similar. Neither can be fully understood in isolation from the other. Special relativity, therefore, deepens the answer to what magnetism actually is. Magnetism is not simply an additional force sprinkled on top of electricity. Electric and magnetic effects are intertwined aspects of one electromagnetic structure, and the way those aspects appear depends partly on the motion of the observer. Yet even this elegant picture leaves something unexplained. A current-carrying wire contains charges that are visibly moving on a macroscopic level, so its magnetic field fits naturally into the classical electromagnetic description. A permanent magnet is different. Inside magnetized iron, there does not need to be an ordinary electrical current circulating around the object. Instead, much of its magnetism arises from properties of electrons that classical physics never anticipated. Electrons possess intrinsic angular momentum called spin. They possess associated magnetic moments, and under the right conditions, enormous numbers of these quantum magnetic moments can influence one another and organize collectively. Relativity reveals why electricity and magnetism cannot truly be separated. Quantum mechanics reveals why matter itself can become magnetic. And together, those two ideas begin to explain why such an ordinary object as a small magnet can contain physics reaching from moving electric charges all the way down to the fundamental structure of quantum particles. To understand why an ordinary piece of matter can become magnetic, we have to leave behind wires, coils, and visible electric currents, and look much deeper inside the atom. That change in scale was only possible once physicists discovered that atoms themselves contain electrically charged particles. In 1897, Joseph John Thomson provided compelling evidence for the existence of the electron. His experiments with cathode rays showed that atoms were not indivisible pieces of matter after all. They contained much smaller negatively charged components. That discovery immediately gave electricity a microscopic foundation. Electric current was no longer simply something mysterious flowing through a wire. It could be understood as the organized motion of electric charge, and electrons were among the particles carrying that charge. A little more than a decade later, Ernest Rutherford helped transform the picture of the atom again. Experiments carried out by Hans Geiger and Ernest Marsden under Rutherford's direction involved firing alpha particles at extremely thin gold foil. Most passed through with only small deflections, while a tiny fraction scattered through surprisingly large angles. Rutherford concluded that most of an atom's positive charge and mass must be concentrated in an extremely small central nucleus. By 1911, the atom had begun to acquire a recognizable structure. There was a compact, positively charged nucleus, surrounded somehow by negatively charged electrons. And because those electrons carry electric charge, they naturally interact with electric and magnetic fields. This led to an appealing early idea about atomic magnetism. If moving electric charge produces a magnetic field, perhaps electrons moving around atomic nuclei behave somewhat like tiny electrical currents. Imagine charge travelling continuously around a circular loop of wire. That loop produces a magnetic field and behaves like a small magnetic dipole, with a magnetic moment describing both the strength and orientation of its magnetism. So if an electron travelled around an atomic nucleus in a closed orbit, perhaps its motion would also create a magnetic moment. There is genuine physics hidden inside this intuition. The problem is that an atom is not actually a miniature solar system. Electrons do not simply circle their nuclei along neat classical trajectories in the way planets orbit the Sun. That difficulty became impossible to ignore during the development of quantum mechanics. In 1913, Niels Bohr proposed an important transitional model of the atom. Bohr allowed electrons to occupy only certain permitted orbits with particular energies. An electron could move between these allowed states by absorbing or emitting a specific amount of energy. The Bohr model successfully explained important features of the hydrogen spectrum and introduced quantization into atomic structure. But it was still partly built around the image of electrons travelling along definite paths. Quantum mechanics eventually replaced that picture. During the 1920s, Erwin Schrödinger developed wave mechanics, in which the state of an electron is described by a wave function rather than by a classical orbit with a precisely defined path. An electron in an atom occupies a quantum state. That state can tell us the probabilities associated with measurements of position, energy, angular momentum, and other observable properties. But in general, it does not describe a tiny particle endlessly tracing out a little planetary circle around the nucleus. This matters enormously for magnetism. The classical current loop analogy is useful for developing intuition, but the actual magnetic behaviour of electrons inside atoms must be calculated using quantum mechanics. One important ingredient is orbital angular momentum. In classical physics, angular momentum is naturally associated with something moving around an axis or following an orbit. Quantum mechanics retains the concept of angular momentum, but gives it a very different structure. Atomic electron states can possess quantist orbital angular momentum. That means the possible values are restricted rather than varying continuously. Because the electron carries electric charge, orbital angular momentum is associated with an orbital magnetic moment. So there really is a connection between the electron's atomic state and magnetism. But it is not necessary to imagine the electron as a little marble racing around a circular track. The magnetic moment belongs to the quantum state itself. Different atomic orbitals possess different amounts and arrangements of orbital angular momentum. Some states can contribute significantly to an atom's magnetic behaviour, while in other situations orbital contributions partly cancel or become strongly constrained by the surrounding atomic environment. And this helps explain why different elements behave so differently in magnetic fields. Atoms contain different numbers of electrons. Those electrons occupy different quantum states. Their orbital magnetic contributions can add together, oppose one another, or largely cancel. Already, magnetism is becoming a question not simply of whether charge exists, but of how quantum states containing charged particles are arranged. Yet even this is not enough. Experiments revealed magnetic behaviour that could not be fully explained through orbital angular momentum alone. Electrons possess another form of angular momentum. It is called intrinsic spin. The name is slightly dangerous because it sounds wonderfully mechanical. It invites us to picture an electron as a tiny ball rotating around its own axis. That picture does not work. As far as modern experiments can determine, the electron behaves as an elementary particle without a known internal rotating surface. Its spin is an intrinsic quantum property, something the electron possesses simply by being the type of particle that it is. And spin comes with its own magnetic moment. This means that even an electron whose magnetic behaviour cannot be explained as charge travelling around an atomic orbit can still possess magnetism. That is the crucial step. The magnetism of ordinary materials is not merely the large-scale result of countless little classical currents hidden inside atoms. It depends on quantum properties that have no exact classical equivalent. Electron charge matters. Orbital angular momentum matters. But intrinsic spin turns out to be one of the most important ingredients of all, And once enormous numbers of these tiny quantum magnetic moments begin interacting with one another inside matter, their collective behaviour can eventually become strong enough for us to feel it directly between two magnets held in our hands. If orbital motion were the only source of magnetism inside atoms, the story would already be complicated enough. But electrons possess another magnetic property that does not come from travelling around the nucleus at all. It comes from something called spin. Spin is one of the intrinsic properties of an electron. It is a form of angular momentum. But the word can be misleading because it immediately suggests a familiar mechanical picture. It is tempting to imagine an electron as a tiny ball rotating rapidly around its own axis, much as Earth spins once every day. That is not what quantum spin means. As far as experiments can determine, the electron behaves as an elementary particle with no known extended surface that could literally rotate. Its spin is built into the quantum description of the particle itself. An electron does not need to be physically spinning in space in order to possess angular momentum. This strange property began to reveal itself experimentally before physicists fully understood what they were seeing. In 1922, Otto Stern and Walther Gerlach performed an experiment that became one of the most famous demonstrations of quantization. They heated silver in an oven to produce a beam of silver atoms and sent that beam through a specially shaped, non-uniform magnetic field. If the magnetic moments of the atoms could point in any direction, as classical physics suggested, the magnetic field should have deflected different atoms by different amounts. The beam should therefore have spread into a continuous distribution. That did not happen. Instead, the silver atoms separated into two distinct beams. The result showed that the relevant angular momentum could not simply take any orientation it pleased. At the quantum scale, certain measurable components of angular momentum appeared only in discrete possibilities. Nature had refused to provide the smooth range of answers classical physics expected. The Stern-Gerlach experiment was performed before the modern concept of electron spin had been introduced, and its historical interpretation developed as quantum theory itself evolved. We now understand that the characteristic two-way splitting of silver atoms is associated with the angular momentum of an unpaired electron, with electron spin playing the essential role. A few years later, in 1925, George Eugene Uhlenbeck and Samuel Abraham Goudsmit proposed that the electron possessed an intrinsic angular momentum of its own. They called this property spin. The idea helped explain puzzling features of atomic spectra that existing models could not account for satisfactorily. But the name again carried a dangerous visual implication. A classical spinning charged sphere would face serious problems if treated as a literal model of an electron. The required mechanical picture simply does not reproduce what quantum theory says an electron is. Spin therefore has to be accepted on its own terms. An electron belongs to a class of particles with spin 1/2. This does not mean that it rotates halfway around something. It refers to the mathematical structure of its intrinsic angular momentum and to the distinctive way its quantum state behaves under rotations. One of the physicists who played a central role in understanding this unusual two-valued behaviour was Wolfgang Ernst Pauli. Before electron spin had been fully formulated, Pauli had already introduced a two-valued quantum property to account for features of atomic structure. He also developed the exclusion principle, which states that two identical electrons in the same atom cannot occupy exactly the same quantum state. Spin later became an essential part of describing how that principle works. Within a given atomic orbital, for example, two electrons can occupy the same spatial state provided their spin states differ. In simplified language, these are often described as spin up and spin down. Those names do not mean that tiny electrons are physically pointing like microscopic arrows in two fixed directions at all times. They refer to possible measurement outcomes for a chosen component of spin. This intrinsic angular momentum is deeply connected to magnetism. Because the electron carries electric charge, its spin is associated with an intrinsic magnetic dipole moment. In practical terms, an electron behaves as though it possesses its own tiny magnetic orientation. Place it in a magnetic field, and the energy of the electron can depend on how its spin magnetic moment is oriented relative to that field. This is one reason magnetic fields can split atomic energy levels and influence the spectra produced by atoms. It also means something more fundamental. An electron does not need to orbit a nucleus like a miniature planet in order to contribute to magnetism. Even its intrinsic quantum identity carries a magnetic moment. The natural scale for expressing electron magnetic moments is called the Bohr magneton, named after Niels Bohr. A single Bohr magneton is extraordinarily small on an everyday scale, roughly 9.3 times 10 to the minus 24 joules per Tesla. That number is almost absurdly tiny from the perspective of human experience. But a visible piece of matter contains an enormous number of electrons. A small object containing only a few grams of material can easily contain numbers of atoms on the order of 10 to the power of 22 or 10 to the power of 23. When microscopic magnetic moments mostly cancel, their combined external effect can be extremely weak. But if enough of those moments become organized in a common direction, something very different happens. An effect belonging to individual quantum particles can become large enough to lift metal objects, turn motors, hold doors closed, or make two magnets push against your fingers. This is the remarkable bridge between quantum physics and everyday magnetism. At one end is a single electron possessing an intrinsic magnetic moment so small that ordinary senses could never detect it. At the other is a permanent magnet whose force can be felt directly. The difference is not that the individual electrons somehow become enormously more magnetic. It is that matter can contain staggering numbers of them, and under the right conditions, their tiny quantum magnetic moments do not simply disappear into a disorderly crowd. They can interact, organize, and begin behaving collectively. Electron spin, therefore, provides one of the essential microscopic ingredients of magnetism. It is not classical rotation. It is not a miniature current loop in the ordinary mechanical sense. It is an intrinsic quantum property of the electron itself, inseparably linked to a tiny magnetic moment. And once that tiny moment is multiplied across immense numbers of electrons inside matter, the invisible force of magnetism begins to emerge on a scale large enough for us to hold in our hands. Once the electron's spin had been recognized as a source of magnetism, physicists were left with a more precise question. Exactly how magnetic should an electron be? At first, this might sound like the sort of detail that only matters deep inside a physics laboratory, but the answer became one of the most successful tests of quantum theory ever made. The key figure was the British physicist Paul Adrian Maurice Dirac. In the late 1920s, Dirac developed a new equation describing electrons in a way that combined quantum mechanics with Albert Einstein's special theory of relativity. This was a major achievement. Earlier quantum mechanics could describe many atomic phenomena extremely well, but it did not fully incorporate the requirements of special relativity. Dirac wanted a theory that could do both. When he succeeded, something remarkable happened. Electron spin appeared naturally within the theory. It did not need to be added afterwards as an extra mechanical feature. The mathematical structure of the relativistic quantum electron already contained the behaviour associated with spin, and with that spin came a prediction for the electron's magnetic moment. To describe the connection between an electron's spin and its magnetism, physicists use something called the G-factor. The name sounds rather more mysterious than the idea itself. The G-factor is essentially a proportionality number. It tells us how strongly a particle's magnetic moment is related to its angular momentum. If two particles carried the same amount of angular momentum but had different G-factors, their magnetic responses could differ. For the electron, Dirac's theory predicted a G-factor of exactly 2. That prediction was astonishingly close to reality, but not perfectly exact. As measurements improved, physicists discovered that the electron behaved as though its G-factor was slightly larger than 2. The difference is tiny. Yet that tiny difference turned out to reveal an entire hidden layer of quantum physics. The deviation is usually discussed through something called the anomalous magnetic moment of the electron. The word anomalous does not mean that something has gone wrong with the electron. It simply refers to the difference between the simplest Dirac prediction and the more complete value produced by quantum field effects. The crucial point is that an electron cannot be treated as though it exists entirely alone. In quantum electrodynamics, the electron interacts continuously with the quantum electromagnetic field. Even in what we casually call empty space, the quantum field cannot simply be ignored. When physicists calculate the magnetic properties of the electron more precisely, they have to include the effects of these interactions. One of the first major breakthroughs came from Julian Seymour Schwinger. During the development of quantum electrodynamics in the late 1940s, Schwinger calculated the leading correction to the electron's magnetic moment. His results showed that the tiny departure from Dirac's value could be explained by the electron's interaction with the electromagnetic quantum field. The correction depends on a fundamental quantity called the fine structure constant, which measures the strength of the electromagnetic interaction. The leading contribution calculated by Schwinger is small, only a little more than 1 part in 1,000 when expressed in the conventional anomalous magnetic moment. But experimental measurements were precise enough to detect it. And as both theory and experiment became more sophisticated, the comparison became extraordinary. Physicists calculated additional corrections involving increasingly complicated quantum processes. In the mathematical language of quantum electrodynamics, the electron can interact with the electromagnetic field through processes represented by increasingly elaborate diagrams. These calculations include effects associated with virtual photons and, at higher orders, contributions involving other virtual particle processes. It is important not to imagine these diagrams too literally as tiny classical events happening along definite paths. They are tools used to calculate quantum probabilities and corrections. What matters is the final prediction. Modern quantum electrodynamics predicts the magnetic moment of the electron with remarkable precision, and laboratory measurements test that prediction to an equally remarkable level. Experiments involving individual electrons trapped and controlled with electromagnetic fields have allowed the electron magnetic moment to be measured to parts per trillion. That is an almost absurd degree of accuracy. Imagine measuring the distance around Earth and achieving a comparable fractional precision. The permitted error would be extraordinarily small compared with the scale of the planet. This is why the electron's magnetic moment has become one of the great precision tests of fundamental physics. A property that begins as something as simple sounding as how magnetic an electron is turns out to depend on the full quantum description of the electromagnetic interaction. The electron is not merely assigned a magnetic strength and left alone. Its measured magnetism reflects its relationship with the quantum field surrounding it. This also gives us a much deeper way to think about the magnetism found inside ordinary matter. When an electron contributes a tiny magnetic moment to an atom, that property is not the result of some crude microscopic mechanism hidden inside the particle. It is an intrinsic quantum characteristic whose precise value is shaped by relativistic quantum field theory. Paul Adrian Maurice Dirac's original prediction already came remarkably close. Julian Seymour Schwinger's correction brought theory closer still, and decades of increasingly precise calculations and experiments have continued refining that agreement. There is something almost calming about how unforgiving the comparison is. If quantum electrodynamics were even slightly wrong in the way it describes the electron's interaction with the electromagnetic field, the discrepancy could appear in this tiny magnetic measurement. Instead, theory and experiment continue to agree with extraordinary precision. So the magnetic moment of an electron is far more than a miniature version of the magnetism we feel between two bar magnets. It is one of the clearest places where relativity, quantum mechanics, electric charge, spin, and the electromagnetic quantum field all meet. And hidden inside that almost unimaginably small magnetic effect is some of the most precisely tested physics human beings have ever produced. At this point, magnetism has already taken us far beyond the simple image of two metal objects pulling on one another. We have seen that electric and magnetic fields belong to a single electromagnetic structure. We have seen that electrons carry charge, possess intrinsic spin, and have tiny magnetic moments. And we have seen that even the precise strength of an electron's magnetism depends on subtle quantum effects. To describe all of this at the deepest experimentally established level, modern physics uses quantum electrodynamics. Quantum electrodynamics is the quantum field theory of electrically charged particles interacting with the electromagnetic field. Its modern form emerged during the middle of the 20th century through the work of several physicists, including Richard Phillips Feynman, Shinichiro Tominaga, Julian Seymour Schwinger, and Freeman John Dyson. Feynman, Tominaga, and Schwinger developed powerful methods for calculating electromagnetic quantum interactions, while Dyson helped show how apparently different formulations of the theory were connected. The result became one of the most successful theories ever constructed. The central shift is subtle but profound. In classical electromagnetism, the electromagnetic field is treated as a continuous field extending through space. Quantum electrodynamics keeps the field but quantizes it. The electromagnetic field becomes a quantum field, and the particles we call photons are quantist excitations of that field. This immediately raises an obvious question. If photons are the quanta of the electromagnetic field, is magnetism simply made of photons? Not quite. That statement is tempting because it compresses a complicated idea into something easy to picture, but taken literally, it becomes misleading. A photon is a real quantum excitation of the electromagnetic field. Visible light consists of photons. Radio waves, microwaves, ultraviolet radiation, X-rays, and gamma rays are also manifestations of the same electromagnetic field, described quantum mechanically in terms of photons. But a static magnetic field around a permanent magnet should not be imagined as billions of little photon bullets continuously streaming outward from the metal. If that were the picture, a magnet would appear to be constantly radiating energy away simply by existing. That is not what happens. A permanent magnet can maintain a nearly static magnetic field without continuously losing energy as electromagnetic radiation. The magnetic field is better understood as a particular configuration of the electromagnetic field. Quantum electrodynamics describes that field quantum mechanically, But not every field configuration corresponds to a collection of ordinary detectable photons flying through space. This is where discussions of virtual photons often appear. In quantum calculations, interactions between charged particles can be represented using mathematical terms that are conveniently pictured through Feynman diagrams. Within those calculations, one often speaks of virtual photons being exchanged between charged particles. This language is extremely useful. But it should not be taken too literally. A virtual photon is not simply a tiny invisible version of a real photon travelling secretly between two magnets along a definite path. Virtual particles are internal elements of a perturbative calculation. They help physicists organise the possible contributions to an interaction, but they are not directly observable particles in the same sense as photons detected by a telescope or laboratory instrument. So when physicists say electromagnetic forces can be described through photon exchange, they are describing the structure of quantum electrodynamics. They are not saying that two stationary magnets are firing measurable streams of light particles at one another. The real photon itself is nevertheless fundamental. Photons have no rest mass. That matters because the mass of a force-carrying field is closely related to the range of the interaction it mediates. A field associated with a massive mediator generally produces interactions that become strongly suppressed over sufficiently large distances. The electromagnetic field is different. Because the photon is massless, electromagnetic interactions can extend across enormous distances. Their strength weakens as objects become more widely separated, but there is no intrinsic short-distance cutoff imposed by a photon rest mass. This is why electromagnetic fields can operate across atomic scales, laboratory scales, planetary distances, and even astronomical distances. Light from distant galaxies can cross space for billions of years. Earth's magnetic field extends far beyond the solid surface of the planet. The Sun's electromagnetic influence reaches throughout the solar system. All of these phenomena belong to the same underlying field, and this gives us a clearer answer to the question of what a magnetic field actually is. It is not an additional material substance placed inside space. It is one aspect of the electromagnetic quantum field. At the classical level, we often separate this field into electric and magnetic components because that description is extremely useful. At the quantum level, the electromagnetic field is the more fundamental object. Its interactions with electrically charged quantum fields give rise to the electromagnetic phenomena we observe. The electron is especially important because it carries electric charge and possesses intrinsic spin. Its quantum state therefore interacts with the electromagnetic field in ways that include both electric and magnetic effects. Inside matter, enormous numbers of electrons occupy quantum states determined by atomic structure, chemical bonding, crystal environments, and interactions with other electrons. Those arrangements decide whether the tiny magnetic contributions from individual electrons mostly cancel, respond weakly to an external field, or organize collectively into a strongly magnetic material. This distinction is essential. Quantum electrodynamics tells us what electromagnetic interaction fundamentally is, but it does not mean that every visible magnetic behaviour can be understood merely by saying the word photon. The reason iron can become strongly magnetized, while glass ordinarily cannot, depends on the detailed quantum organization of matter. The reason a permanent magnet keeps its magnetization depends on collective electron behaviour, magnetic domains, crystal structure, and the energetic stability of those arrangements. The electromagnetic field provides the fundamental interaction. The quantum states of matter determine what form that interaction takes in a particular material. So at the deepest level supported by modern experiment, Magnetism is not made from a separate magnetic ingredient. It belongs to the electromagnetic quantum field. Photons are the quantist excitations of that field. Electrically charged particles interact through it, and the magnetism we encounter in ordinary matter emerges from the way quantum particles, especially electrons, carry charge, possess magnetic moments, and organize themselves within that electromagnetic reality. The familiar force between two magnets is therefore not the surface expression of some hidden magnetic fluid. It is a macroscopic consequence of one of the fundamental quantum fields of nature. If electrons possess magnetic moments, and almost every ordinary material contains vast numbers of electrons, then a natural question appears. Why is almost everything around us not strongly magnetic? A wooden table contains electrons. So does a glass window, a copper wire, a plastic bottle, and a drop of water. Each electron carries electric charge, possesses intrinsic spin, and can contribute to magnetic behaviour. Yet most of these objects do not cling to the refrigerator door. The reason is that the existence of microscopic magnetic moments is only the beginning of the story. What matters just as much is how those moments are arranged. Inside an atom, electrons occupy quantum states according to strict rules. One of the most important was formulated by Wolfgang Ernst Pauli in 1925. The Pauli exclusion principle states that no two identical electrons in an atom can occupy exactly the same quantum state. This has enormous consequences for atomic structure. Electrons fill available states in organized patterns. Within many atomic orbitals, electrons can form pairs whose spin contributions point in opposite measurable directions. When two electrons occupy such paired states, their spin magnetic moments can largely cancel one another. The same general principle applies to orbital magnetic contributions as well. Depending on the electronic structure of an atom, different magnetic moments can combine in ways that leave very little overall magnetism. This is especially important in atoms with closed electron shells. A closed shell is a completely filled set of allowed electronic states. Because the electrons occupy the available states in balanced arrangements, the total angular momentum and magnetic moment of a closed shell often cancel to a very small value. So an atom may contain many individual electrons, each fundamentally magnetic, while the atom as a whole behaves as though it possesses almost no permanent magnetic moment. It is a little like having a room full of people pulling equally hard in opposite directions. There is plenty of effort happening internally, but from outside, very little moves. This cancellation helps explain why many substances show no obvious permanent magnetism, but it does not mean they are completely unaffected by magnetic fields. One of the weakest and most widespread forms of magnetic behaviour is called diamagnetism. When an external magnetic field is applied to matter, it can slightly modify the orbital motion and quantum states of electrons. These changes create an induced magnetic response that tends to oppose the applied magnetic field. In other words, a diamagnetic material is weakly repelled by a region of stronger magnetic field. Diamagnetism occurs, at least in principle, in all ordinary materials. Usually the effect is so weak that we never notice it in everyday life. A fridge magnet placed beside a glass of water will not send the glass sliding dramatically across the kitchen counter, but some substances display stronger diamagnetic responses than others. Bismuth is a well-known example. Another is pyrolytic graphite, a specially structured form of carbon with unusually strong diamagnetic behaviour. With sufficiently strong permanent magnets arranged carefully beneath it, a small piece of pyrolytic graphite can actually levitate. The effect is real, although it is rather less useful for making the sofa float. There is another important form of weak magnetism called paramagnetism. Paramagnetic materials contain atoms or ions with unpaired electrons. Because these electrons are not paired with partners whose magnetic moments cancel them, the atoms can possess a net magnetic moment. When no external magnetic field is present, however, these microscopic moments are usually oriented in many different directions. Their combined effect therefore remains small. Apply an external magnetic field, and the magnetic moments tend to favour orientations that align more closely with that field. The material becomes weakly magnetised. Unlike diamagnetism, which generally produces a response opposing the applied field, paramagnetism tends to reinforce it. The effect is still usually modest. The reason is thermal motion. At any temperature above absolute zero, atoms and molecules possess thermal energy. That continual microscopic agitation works against the tendency of magnetic moments to remain neatly aligned. The external field encourages order. Thermal motion encourages disorder. At ordinary temperatures, the competition means that only a small preference for alignment usually develops in a paramagnetic substance. Remove the magnetic field, and thermal motion rapidly randomizes the orientations again. The material loses almost all of the magnetization that had been induced. This explains why a piece of paramagnetic material does not normally become a lasting permanent magnet simply because it has briefly been exposed to a magnetic field. Aluminium is a familiar example of a paramagnetic material, although its response is weak enough to be practically invisible in most everyday situations. Oxygen molecules are also paramagnetic because their electronic structure contains unpaired electrons. In sufficiently strong laboratory magnetic fields, even liquid oxygen can show striking magnetic behaviour. The important lesson is that the word magnetic covers several different physical responses. Diamagnetic materials weakly oppose an applied field. Paramagnetic materials weakly favour alignment with it. And many atoms contain electron magnetic moments that mostly cancel before any large-scale magnetic behaviour can emerge. So simply containing electrons is not enough to make a permanent magnet. Even possessing unpaired electrons is not enough. For strong permanent magnetism, something more dramatic has to happen. Large numbers of microscopic magnetic moments must begin influencing one another so that their orientations become correlated across substantial regions of the material. Instead of behaving like isolated tiny magnets pointing randomly, they must develop collective order. That requires interactions between electrons. And in certain materials, those interactions are strong enough to overcome much of the disorder that would otherwise keep the magnetic moments pointing in different directions. This is why iron behaves so differently from glass, even though both are made from atoms containing electrons. The crucial difference is not whether microscopic magnetism exists. It is whether quantum mechanics allows those microscopic magnetic moments to cooperate. Only when that collective organization appears can the almost unimaginably small magnetic moment of an individual electron become part of a magnetic field strong enough to feel with your own hand. Iron is one of the materials that gives magnetism its familiar everyday character. Bring a strong magnet near an iron object and the response can be immediate. The iron is attracted. Under the right conditions, it can even become magnetized itself. This strong behavior belongs to a phenomenon called ferromagnetism. Ferromagnetism is very different from the weak responses found in diamagnetic or paramagnetic materials. It involves the collective organization of enormous numbers of atomic magnetic moments, allowing their tiny individual contributions to reinforce one another across substantial regions of matter. Iron is especially suited to this because of the arrangement of its electrons. its atomic electron structure contains partially filled states with unpaired electrons. Those unpaired electrons contribute magnetic moments, particularly through their intrinsic spin. If the magnetic moments of all those atoms pointed randomly, however, their effects would still mostly cancel on a large scale. Something has to encourage neighbouring moments to coordinate. That something is known as the exchange interaction. The quantum mechanical foundations of this effect were developed during the 1920s, with Werner Karl Heisenberg playing a central role in explaining how exchange could produce ferromagnetic ordering. The word interaction can make it sound as though physicists discovered an entirely new force of nature acting between neighbouring electrons. They did not. The exchange interaction is not an additional fundamental force alongside electromagnetism, gravity, or the strong and weak nuclear interactions. Instead, it emerges from the combination of ordinary electromagnetic interactions between electrons and some very unusual rules of quantum mechanics. One of those rules is the Pauli exclusion principle. Electrons are identical quantum particles belonging to a class called fermions. When two identical fermions are described together, their combined quantum state must have a particular mathematical property called antisymmetry. In simple terms, exchanging the identities of two identical electrons changes the sign of their combined quantum wave function. That sounds abstract, but it has very real consequences. The spatial arrangement of electrons and the arrangement of their spins cannot be chosen independently in every situation. Because the full quantum state has to obey this antisymmetry requirement, certain spin configurations correspond to different spatial distributions of the electrons. And spatial distribution matters because electrons repel one another electrically. If one allowed arrangement keeps electrons, on average, farther apart than another, their electrostatic interaction energy can differ. The result is that quantum mechanics can make some relative spin configurations energetically more favourable than others. In many ferromagnetic materials, the relevant electronic structure favours neighbouring magnetic moments tending toward parallel alignment. This is the exchange interaction at work. It is important to notice how different this is from imagining two tiny bar magnets simply twisting one another into line. Ordinary magnetic dipole forces between individual electron moments are generally far too weak to explain the strong ordering found in ferromagnets. The dominant mechanism comes from quantum mechanics, the electromagnetic interaction between electrons, and the strange statistical rules governing identical particles. When the exchange interaction favours parallel alignment strongly enough, something remarkable can happen. The material can develop spontaneous magnetization. Spontaneous magnetization means that a region of the material can possess an organized magnetic orientation, even when there is no external magnetic field forcing it into place. The electrons are not waiting for a nearby bar magnet to tell them what to do. Their own quantum interactions make collective alignment energetically favourable. That is one reason ferromagnetism feels so different from paramagnetism. In a paramagnetic material, an external field encourages magnetic moments to line up, but thermal motion usually scrambles much of that alignment again. In a ferromagnet, the interactions between neighbouring moments can themselves maintain long-range magnetic order. Temperature still matters enormously. Atoms in a warm solid are not sitting perfectly still. They vibrate, and the magnetic degrees of freedom also experience thermal fluctuations. As temperature rises, this randomizing influence becomes stronger. The competition between magnetic ordering and thermal disorder was investigated extensively by Pierre Curie. The characteristic temperature at which a ferromagnetic material loses its long-range ferromagnetic order is called the Curie temperature. Below this temperature, exchange interactions can support collective magnetic order. Above it, thermal agitation becomes strong enough that sustained ferromagnetic alignment disappears, and the material becomes paramagnetic. For iron, the Curie temperature is roughly 770 degrees Celsius. That is extremely hot by everyday standards, but it gives a useful picture of how robust the underlying magnetic ordering can be. Heat an iron magnet sufficiently, and eventually the organized arrangement of magnetic moments breaks down. Cool it below the Curie temperature again, and ferromagnetic ordering can become possible once more, although the final large-scale magnetization depends on how the material cools and on its magnetic history. This immediately shows why permanent magnetism cannot be understood simply by drawing little current loops inside matter. Classical electromagnetism can explain why moving electric charge produces a magnetic field. It can explain forces between currents and the behaviour of fields around wires, but it does not explain why billions upon billions of microscopic magnetic moments inside a solid should spontaneously prefer correlated orientations. That requires quantum mechanics. The Pauli exclusion principle matters. The indistinguishability of electrons matters. The anti-symmetry of their combined quantum states matters. Their electrostatic interaction matters. And from those ingredients emerges the exchange interaction capable of organizing magnetic moments across a material. Even then, a piece of iron does not automatically behave like one perfectly aligned giant magnet. Different regions can settle into different magnetic orientations, allowing much of their external magnetism to cancel. But within those regions, the underlying ferromagnetic order is already present. So when iron responds dramatically to a magnet, the explanation reaches far below the visible metal. Its electrons are not simply miniature compass needles. They are quantum particles obeying rules with no true classical equivalent. And those rules allow enormous numbers of tiny magnetic moments to cooperate, turning the barely measurable magnetism of individual electrons into one of the strongest magnetic effects we encounter in ordinary matter. A piece of iron can contain enormous numbers of locally aligned magnetic moments and still appear almost completely unmagnetized from the outside. At first that seems contradictory. If ferromagnetism encourages neighbouring electron magnetic moments to point in similar directions, then why does every ordinary piece of iron not behave like a powerful permanent magnet? The answer is that magnetic order does not necessarily extend through the entire object in one single direction. Instead, ferromagnetic materials often divide themselves into regions called magnetic domains. The idea was developed around the beginning of the 20th century by the French physicist Pierre Weiss. Within a magnetic domain, large numbers of atomic magnetic moments are aligned in roughly the same direction. Each domain can therefore be strongly magnetized internally. But neighbouring domains do not necessarily point the same way. One region may be magnetized toward the left, another may point toward the right. Others may favour still different directions allowed by the material's crystal structure. If those different contributions largely balance one another, the magnetic field outside the entire object can be quite small. So an apparently unmagnetized piece of iron is not necessarily magnetically disordered at the atomic scale. It can contain highly ordered regions whose effects simply cancel when viewed from farther away. This arrangement is energetically useful. If an entire large piece of ferromagnetic material were magnetized uniformly in one direction, it could produce a substantial magnetic field extending into the surrounding space. That field contains energy. By breaking into domains pointing in different directions, the material can often reduce the energy associated with its external magnetic field. The boundaries between neighbouring domains are called domain walls. A domain wall is not an infinitely sharp dividing line where every magnetic moment suddenly flips direction. Instead, it is a transition region. Across the wall, the preferred orientation of the magnetization gradually changes from the direction favoured in one domain to the direction favoured in the next. The detailed thickness and structure of a domain wall depend on the material and on the competition between several forms of energy, including exchange interactions and magnetic anisotropy. Now imagine placing this piece of iron in an external magnetic field. The domains whose magnetization already points roughly along the applied field become energetically more favourable. Their boundaries can begin to move. A favourably aligned domain may expand, while a neighbouring domain pointing in a less favourable direction shrinks. The magnetization within domains can also rotate toward the applied field. Gradually, the balance changes. What began as a patchwork of differently oriented regions becomes increasingly dominated by magnetic moments pointing in the same general direction. This is how an external magnetic field can magnetize a ferromagnetic material without physically rearranging the entire solid. The atoms remain in the material, but the magnetic organization inside it changes. If the applied field becomes strong enough, most of the magnetic moments that are able to align will already be oriented as favorably as possible. The material then approaches saturation magnetization. Beyond this point, making the external field stronger produces relatively little additional magnetization because there is simply not much more alignment left to achieve. But something especially important happens when the external field is removed. The material does not always return to exactly the state it occupied before. Some of the domain arrangement created by the applied field may remain. This memory of previous magnetization is part of a phenomenon called magnetic hysteresis. If the applied magnetic field is gradually increased, decreased, reversed, and increased again, the magnetization of a ferromagnetic material does not follow exactly the same path in each direction. Its present magnetic state depends partly on its previous magnetic history. After the external field has been reduced to zero, the magnetization that remains is called remnant magnetization, or remanence. This is one of the properties that makes permanent magnets possible. A material with substantial remanence can retain a significant degree of magnetic organization even after the field that originally magnetized it has disappeared. But retaining magnetization is only part of the requirement. A useful permanent magnet should also resist being easily demagnetized. That resistance is described by coercivity. A material with high coercivity requires a relatively strong opposing magnetic field before its magnetization can be driven substantially back toward zero. A material with low coercivity can change its magnetic state much more easily. This distinction is extremely useful in technology. Soft magnetic materials have relatively low coercivity. Their magnetization can be changed readily, which makes them valuable in devices such as transformer cores and electromagnets, where the magnetic state needs to respond repeatedly to changing electrical currents. Hard magnetic materials have higher coercivity and are much better suited to permanent magnets. Their internal magnetic organization is harder to disturb. Crystal defects, grain boundaries, internal stresses, and the detailed structure of a material can all influence how easily domain walls move. If domain walls become pinned by features inside the material, returning to a completely different magnetic arrangement may require overcoming significant energy barriers. This also answers one of the most natural questions about permanent magnets. If a magnet can exert forces year after year, where does its energy come from? A permanent magnet does not need to consume energy continuously merely to maintain a static magnetic field. Its magnetized state can be a stable or long-lived metastable arrangement of the material. Metastable means that the configuration may not be the only possible state, or even the absolute lowest energy state under every circumstance, but substantial energy barriers prevent the system from easily reorganizing itself. The magnetic moments therefore remain collectively arranged without requiring a continuous supply of electrical power. This is similar in spirit to many stable structures around us. A book sitting on a shelf does not need a battery to remain on the shelf. A crystal does not continuously burn fuel to preserve its lattice. Once matter settles into a sufficiently stable configuration, it can remain there for a very long time unless something disturbs it. A permanent magnet is more subtle, but the same broad idea applies. Heat can disturb the magnetic order. A sufficiently strong opposing magnetic field can reorganize domains. Mechanical shocks can sometimes assist domain rearrangement in certain materials. But under ordinary conditions, a well-designed permanent magnet can preserve much of its magnetic state for many years. So the visible magnet we hold is not one perfectly uniform army of electrons, all pointing identically from one end to the other. It is a carefully structured collective quantum system. Ferromagnetic interactions create local order. Domains organize that order on larger scales. Domain walls separate competing orientations. External magnetic fields can reshape those domains. Hysteresis allows the material to remember its magnetic history. And coercivity can lock much of that organization in place. The result is a piece of matter that can sit quietly on a table, apparently doing nothing at all, while the quantum magnetic moments inside remain arranged strongly enough to produce a field extending far beyond the material itself. A permanent magnet can seem almost suspiciously persistent. Leave one on a shelf for a year, and it is still magnetic. Leave it there for 10 years, and in many cases it will still pull on iron almost as strongly as before. There is no visible power source, no fuel being consumed, and no internal motor keeping anything in motion. The reason lies not in some endless supply of magnetic energy, but in how difficult it can be for the material's internal magnetic structure to change. A useful permanent magnet needs more than strong magnetization. It also needs stability. One of the most important ingredients behind that stability is called magnetocrystalline anisotropy. Inside a crystalline solid, atoms are arranged in an ordered lattice. The electronic environment around each atom therefore depends on the directions defined by that crystal structure. Because electron spin and orbital behaviour interact with this environment, certain directions can become energetically more favourable for the magnetization than others. These preferred directions are known as easy axes of magnetization. The word easy is relative. It does not mean that magnetic moments are physically sliding around without resistance. It means that, from the point of view of energy, some orientations are more stable than others. If the magnetization points along one of these preferred crystal directions, rotating it away can require additional energy. That creates a kind of built-in resistance to magnetic rearrangement. A good permanent magnet, therefore, does not rely only on having many aligned electron moments. It also benefits from a crystal structure that strongly encourages those moments to remain aligned in particular directions. The microscopic structure of the material matters just as much. Real magnets are not perfect single crystals containing flawless magnetic domains. They contain grains, boundaries between those grains, defects in the crystal lattice, variations in composition, and other structural features. At first, imperfections might sound undesirable. But in permanent magnet design, some of them are extremely useful. A magnetic domain wall trying to move through a material can encounter grain boundaries or structural irregularities that make its motion more difficult. These features can effectively pin the domain wall in place. If domain walls cannot move easily, the magnet cannot easily reorganize itself into a less magnetized state. Particle size can matter as well. By controlling the size and orientation of microscopic grains, manufacturers can influence how easily domains form, move, reverse, or remain locked in place. This is why modern permanent magnets are engineered materials rather than simply lumps of strongly magnetic elements. Their microstructure is carefully controlled. This resistance to magnetic reversal is closely related to coercivity. A magnet with high coercivity requires a strong opposing magnetic field before its magnetization is substantially reversed. That is different from saturation magnetization. Saturation magnetization describes how strongly magnetized a material can become when its available magnetic moments are aligned as fully as possible. A material can have a high saturation magnetization but relatively low coercivity, meaning it can become strongly magnetic but lose or reverse that magnetization fairly easily. For a durable permanent magnet, both strength and stability matter. Some of the most powerful modern permanent magnets achieve this combination using rare earth elements. One especially important material is neodymium iron boron. Its magnetic properties arise from a combination of iron, which provides strong magnetic interactions, and neodymium, whose electronic structure contributes very strong magnetocrystalline anisotropy. The crystal structure of the compound helps lock the magnetization into preferred directions. As a result, neodymium iron boron magnets can be remarkably strong for their size. Small examples can easily snap together hard enough to pinch skin or crack if allowed to collide suddenly. Their surface magnetic fields commonly reach several tenths of a Tesla, and some specially shaped magnets can approach or exceed about 1 Tesla near their surfaces. Earth's magnetic field, by comparison, is typically only several tens of microtesla at the surface. That means the field close to a strong neodymium magnet can be many thousands of times stronger than the magnetic field guiding an ordinary compass. Another important rare earth magnetic material is samarium cobalt. Samarium cobalt magnets are generally more expensive and can be somewhat less powerful than the strongest neodymium iron boron magnets, but they offer excellent magnetic stability and perform particularly well at elevated temperatures. Temperature is one of the great enemies of permanent magnetism. As a magnet becomes warmer, thermal motion increases. The microscopic magnetic moments become increasingly disturbed, and the energetic barriers that help preserve domain arrangements become easier to overcome. At sufficiently high temperatures, magnetization can weaken significantly. Reach the Curie temperature, and long-range ferromagnetic order itself disappears. Even below that point, some permanent magnets can suffer irreversible losses if they are heated beyond the temperature range for which they were designed. Cooling them afterwards does not necessarily restore the original magnetic arrangement. Their domains may have already reorganized. This helps explain why different magnetic materials are selected for different environments. A small neodymium magnet inside an electronic device faces different demands from a magnet operating near a hot engine or inside industrial machinery. The chemistry, crystal structure, grain size, and processing method can all be adjusted to improve stability under particular conditions. And none of this requires a hidden source of power. A permanent magnet is not continuously burning energy to maintain its field. Energy is associated with the magnetized configuration of the material and with the electromagnetic field around it. But a static configuration does not require a continuous energy supply merely to persist. the magnet remains magnetic because changing its internal arrangement can require overcoming substantial energy barriers. In that sense, its magnetic state is locked into the material. Manufacturing a powerful permanent magnet, therefore, involves carefully creating and stabilizing a particular collective state. The material can be heated, shaped, sintered, aligned in a strong external magnetic field, and processed so that its microscopic grains favor a common magnetic direction. What engineers are manipulating at visible scales is ultimately built from quantum physics. Electron spin contributes magnetic moments. Orbital behaviour influences magnetic anisotropy. Exchange interactions help establish magnetic order. Crystal structure determines preferred orientations, and grain boundaries and defects help prevent that order from easily collapsing. So a magnet that remains strong for decades is not quietly generating new magnetism each second. It is preserving an extraordinarily organized quantum state of matter. Its durability comes from the fact that nature has placed energetic obstacles in the way of disorder. And as long as heat, opposing magnetic fields, corrosion, or physical damage do not overcome those obstacles, the tiny magnetic moments inside can remain collectively aligned for a remarkably long time. Ferromagnetism gives us the most familiar picture of magnetic order. Neighbouring magnetic moments tend to favour similar directions, large regions become strongly magnetised, and under the right conditions the material can retain a substantial magnetic field. But nature is not limited to that one arrangement. Electron magnetic moments can organise themselves collectively in several different ways, and some of the most interesting magnetic materials are built from patterns that appear, at first, almost designed to cancel themselves out. One important example is antiferromagnetism. In an antiferromagnetic material, neighbouring magnetic moments tend to align in opposite directions. Imagine a long row of tiny arrows. One points upward, the next downward, the next upward again, and so on. Each individual magnetic moment may be substantial, and the ordering can be extremely precise, yet the overall magnetisation of the material can remain very small because neighbouring contributions largely cancel. This does not mean the material lacks magnetic order. Quite the opposite. An antiferromagnet can possess highly organised internal magnetism while producing almost no large external magnetic field. That distinction became much clearer through the work of the French physicist Louis-Jeugne Flix-Nel. During the 20th century, Nel developed fundamental ideas describing both antiferromagnetism and ferromagnetism, greatly expanding the understanding of how magnetic moments could order inside solids. His work eventually earned him part of the Nobel Prize in Physics in 1970. Temperature plays an important role in antiferromagnetic order, just as it does in ferromagnetism. Below a characteristic temperature, the interactions between magnetic moments can support the ordered alternating arrangement. Above that temperature, thermal agitation becomes strong enough to destroy long-range antiferromagnetic order. This characteristic point is called the Nel temperature. The idea is closely related to the Curie temperature in a ferromagnet. In both cases, there is a competition between interactions that favour magnetic organisation and thermal motion that tends to scramble it. The preferred arrangement is simply different. A ferromagnet favours a net alignment. An antiferromagnet tends toward an alternating pattern that can produce little net magnetisation. There is also a third important possibility called ferrimagnetism. Ferrimagnetism resembles antiferromagnetism because different groups of magnetic moments point in opposite directions. The crucial difference is that the opposing groups do not have equal magnetic strength. One set of moments may be larger than the other. Their contributions therefore fail to cancel completely. The material is left with a net magnetic moment. A useful way to picture this is to imagine two teams pulling in opposite directions. If both teams pull equally hard, the result can balance almost perfectly. That resembles the cancellation in an ideal antiferromagnet. If one team is stronger, however, the forces still oppose one another, but there is a remaining pull in one direction. That resembles ferromagnetism. One of the most historically important ferromagnetic materials is magnetite. Magnetite is an iron oxide that occurs naturally in rocks and can sometimes become strongly magnetized. Naturally magnetized pieces of magnetite are known as lodestones. Long before anyone knew about electrons, quantum mechanics, or magnetic domains, lodestones provided some of humanity's most striking encounters with magnetism. Their ability to attract iron and influence compass needles made them objects of fascination for centuries. We now understand that magnetite contains iron ions occupying different positions within its crystal structure. Magnetic moments associated with different sublattices tend to orient oppositely, but their contributions are unequal. The incomplete cancellation leaves magnetite with a substantial overall magnetic moment, so one of the oldest magnetic materials known to humanity turns out to rely on a sophisticated form of collective quantum ordering. The mechanism that establishes these arrangements can also be subtler than direct interaction between neighbouring magnetic ions. In many magnetic solids, an important process called superexchange helps determine whether nearby moments prefer parallel or opposite orientations. The name can sound as though the interaction is somehow an especially powerful form of exchange. In reality, the key idea is that magnetic ions can influence one another indirectly through an intervening non-magnetic atom. Consider two magnetic metal ions separated by an oxygen ion. The electrons associated with the magnetic ions do not necessarily need to overlap strongly with one another directly. Instead, their quantum states interact through the electronic orbitals of the oxygen between them. Because of the Pauli exclusion principle, electron hopping, orbital geometry, and electromagnetic interactions, certain relative spin arrangements can become energetically preferred. Under many common circumstances, superexchange favours opposite alignment and therefore helps produce antiferromagnetic order. The precise outcome depends on the atoms involved, their electronic structure, and the geometry of the bonds connecting them. Philip Warren Anderson made major theoretical contributions to the understanding of superexchange and magnetic interactions in solids during the 20th century. His work helped show how apparently simple magnetic patterns could emerge from the much deeper quantum mechanics of electrons moving and interacting within crystalline materials. This is an important reminder that the arrows often drawn to represent spins are only a simplified picture of something much richer. Real magnetic materials contain electrons occupying quantum states spread through atomic orbitals and crystal structures. Their charge, spin, orbital behaviour, and quantum statistics all matter. The final magnetic order emerges from the way these ingredients compete with one another. Sometimes the result is ferromagnetism, with moments reinforcing one another. Sometimes it is antiferromagnetism, with neighbouring moments arranged so that their large-scale effects nearly vanish. Sometimes it is ferromagnetism, where opposing magnetic contributions remain unequal and leave a net magnetization. And there are still more complicated possibilities, including spiral arrangements, frustrated magnetic systems, spin glasses, and other forms of collective order. So magnetism is not one microscopic pattern repeated everywhere. It is an entire family of quantum behaviours. The underlying ingredients remain familiar, electrically charged particles, intrinsic spin, orbital magnetic moments, electromagnetic interactions, and quantum mechanics. But by arranging those ingredients differently, matter can produce remarkably different magnetic personalities. A piece of iron, a crystal of antiferromagnetic material, and a naturally occurring lodestone may all be magnetic for different collective reasons. What they share is the same deeper foundation: vast numbers of quantum particles interacting with one another and organizing their tiny magnetic moments into patterns far larger than any individual atom. Superconductivity reveals just how dramatically the magnetic behaviour of matter can change when quantum particles organize themselves in a completely different way. The story began in 1911 with the Dutch physicist Heike Kamerlingh-Onnes. Onnes had become a pioneer in the study of matter at extremely low temperatures. After succeeding in liquefying helium, he was able to cool materials far below anything routinely achieved before. When he cooled mercury to only a few degrees above absolute zero, something remarkable happened. Its electrical resistance suddenly disappeared. Ordinary conductors resist the movement of electric current. Electrons travelling through them lose energy through interactions with the material, producing heat. In the superconducting state, that familiar electrical resistance falls to an immeasurably small value. A current established in a superconducting loop can therefore persist for an extraordinarily long time without the continuous electrical power that would be required to maintain a current in an ordinary resistive wire. At first it was tempting to think that superconductivity was simply perfect electrical conductivity. But another discovery showed that something much deeper was happening. In 1933, Wolfram Meissner and Robert Oxenfeld studied what happened to magnetic fields when certain materials were cooled into the superconducting state. They found that magnetic flux was expelled from the interior. This behaviour became known as the Meissner effect. The distinction is subtle but essential. Imagine a hypothetical material that suddenly acquired exactly zero resistance while a magnetic field was already passing through it. If perfect conductivity were the only property involved, the existing magnetic field could simply remain trapped inside under ideal conditions. A true superconductor behaves differently. When it enters the superconducting state under suitable conditions, it actively establishes currents near its surface that oppose the magnetic field within the bulk material. The result is that magnetic flux is largely expelled. This means superconductivity is not merely an ordinary conductor made infinitely efficient. It is a distinct thermodynamic and quantum state of matter. The microscopic explanation for many conventional superconductors emerged in 1957 through the work of John Bardeen, Leon Neil Cooper, and John Robert Schrieffer. Their theory showed how electrons can behave collectively in a way that would seem unlikely if we considered only ordinary electrical repulsion. Inside a suitable crystal, interactions between electrons and vibrations of the atomic lattice can allow electrons to form correlated pairs known as Cooper pairs. The two electrons in a Cooper pair are not simply glued together like two tiny objects. Their pairing is a quantum phenomenon extending through the material. Large numbers of these pairs can enter a coherent collective quantum state. Once that happens, the electrons are no longer behaving primarily as isolated particles, scattering independently through the crystal. The entire system acquires new quantum properties. This collective state explains both the disappearance of ordinary electrical resistance and much of the unusual magnetic behaviour of conventional superconductors. One especially striking feature is flux quantization. In certain superconducting arrangements, magnetic flux cannot simply take any arbitrary value. Instead, it appears in discrete units. For conventional superconductors, the fundamental magnetic flux quantum is associated with the charge of a Cooper pair rather than with the charge of a single electron. This is a beautifully direct example of quantum mechanics becoming visible on a scale far larger than an atom. A magnetic field that seems smooth and continuous in everyday life can become constrained into quantist structures because the underlying charged matter is behaving coherently. Superconductors themselves are commonly divided into two broad classes. Type 1 superconductors show a relatively complete Meissner effect until the applied magnetic field becomes sufficiently strong to destroy superconductivity. Below that critical field, magnetic flux is strongly excluded from the bulk. Type 2 superconductors behave differently. They possess two important critical magnetic field strengths. At lower fields, they can also expel magnetic flux. But between the lower and upper critical fields, magnetic flux begins penetrating the material through narrow structures called quantist vortices. Each vortex carries a discrete amount of magnetic flux. Superconductivity remains present around these vortices even though magnetic field threads through their centers. The theoretical description of this vortex state was developed by Alexei Alexeyevich Abrikosov during the 20th century. Type 2 superconductors are especially important technologically because many of them can remain superconducting in much stronger magnetic fields than typical Type 1 materials. This makes them useful in powerful superconducting magnets. The same physics also produces some of the most visually memorable demonstrations of superconductivity. Cool an appropriate superconducting material and place it near a strong magnet, and the superconductor can levitate. Part of the explanation comes from the Meissner effect, because the superconducting material generates currents that oppose magnetic field penetration. But many particularly striking levitation demonstrations use Type 2 superconductors, where another phenomenon called flux pinning becomes important. Magnetic vortices can become trapped at defects or irregularities in the material. Moving the superconductor relative to the magnetic field would require those pinned vortices to shift. Because that movement costs energy, the superconductor can become remarkably stable in position. It can hover above a magnetic track, remain suspended below one, or even appear locked at a fixed angle. This is not simply ordinary magnetic repulsion in a more dramatic costume. It is a consequence of superconductivity, quantist magnetic flux, persistent electrical currents, and the pinning of quantum vortices inside the material. The behaviour becomes especially revealing when compared with an ordinary magnet. A permanent magnet maintains its magnetic state because microscopic electron moments are collectively organized and difficult to rearrange. A superconductor responds to magnetism through a completely different quantum organization of charged particles. In one case, collective electron magnetism can create a persistent magnetic field. In the other, a collective quantum state can exclude magnetic flux or confine it into quantist vortices. Both effects ultimately depend on electrons, electromagnetic interactions, and quantum mechanics. What changes is the state those electrons collectively occupy. Superconductivity therefore gives us another glimpse of what magnetism really is. Magnetic fields are not simply properties attached permanently to certain objects. Their behaviour depends on the electromagnetic field and on the quantum state of the matter interacting with it. Change that quantum state profoundly enough, and even something as familiar as a magnetic field can begin behaving in ways that seem almost impossible from the viewpoint of ordinary materials. The same physical laws that allow a tiny piece of iron to become magnetic can also operate on a scale large enough to surround an entire planet. Earth itself is magnetic. This was one of the great insights of William Gilbert, who argued in 1600 that our planet behaves approximately like a giant magnet. His idea helped explain why compass needles consistently align in a preferred direction instead of being mysteriously attracted towards some distant object in the north. But Earth is not literally a giant bar magnet. There is no enormous permanent magnet buried beneath the continents, patiently pointing north and south. In fact, the temperatures deep inside Earth are far too high for ordinary ferromagnetic iron to remain magnetized in the same way as a permanent magnet sitting on a table. The source of Earth's field lies much deeper and depends on moving electrically conducting material. Beneath Earth's rocky mantle is the outer core, beginning roughly 2,900 kilometers below the surface. This outer core is more than 2,000 kilometers thick and consists mainly of liquid iron mixed with nickel and lighter elements. Iron is not only important because we associate it with magnets. In the liquid outer core, its electrical conductivity matters enormously. Electrically conducting fluid is constantly moving there. Heat escapes from Earth's deep interior, while the gradual solidification of the inner core also helps drive compositional buoyancy. Hotter or lighter material tends to rise, while cooler or denser material sinks. This convection keeps the liquid metal in motion. Because the material conducts electricity, those motions can carry electric currents, and electric currents generate magnetic fields. The mechanism that sustains Earth's magnetic field is called the geodynamo. It is not a simple current loop hidden inside the planet. The outer core is a turbulent, rotating ocean of electrically conducting metal, and the magnetic field is generated through a complicated feedback between fluid motion and electromagnetism. Existing magnetic fields influence moving electrical charges in the fluid. The moving conducting fluid generates electric currents. Those currents produce additional magnetic fields. Under suitable conditions, the system becomes self-sustaining. Earth's rotation also plays an important role. Because the planet spins, moving fluid in the outer core is influenced by the Coriolis effect. The Coriolis effect does not create the magnetic field by itself. A rotating planet made from electrically insulating material would not automatically become a geodynamo. Instead, rotation helps organize the convective motion of the conducting fluid into structures that can support a large-scale, persistent magnetic field. The result, when viewed from far away, resembles the field of a magnetic dipole. Near Earth's surface, the magnetic field typically has a strength of roughly 25 to 65 microtesla, depending on location. That is enough to guide a compass, but it is extremely weak compared with many manufactured magnets. A strong neodymium iron boron magnet can produce a surface field of several tenths of a Tesla, so the field close to such a magnet may be thousands or even tens of thousands of times stronger than Earth's field at the surface. Earth compensates by being rather larger than a fridge magnet. Its magnetic influence extends tens of thousands of kilometers into space and much farther in some directions. The familiar idea of magnetic north and south is slightly more complicated than a compass might suggest. Earth's geographic poles are defined by its axis of rotation. The magnetic poles are determined by the geometry of the magnetic field. These locations do not coincide exactly. They also move over time because the flows inside the outer core continually change. A compass needle's north-seeking endpoints roughly toward the Arctic because of the direction of Earth's magnetic field there. In the strict language of magnetic poles, the region near the geographic north behaves like the pole that attracts the north-seeking end of a compass, which corresponds physically to magnetic south polarity. Historical naming conventions have made this sound rather more confusing than the planet probably intended. Earth's magnetic field is also not permanent in its present orientation. The geological record shows that the field has reversed many times. During a geomagnetic reversal, the overall polarity changes so that what had been magnetic north and south effectively exchange roles. Evidence for these reversals is preserved in rocks. When certain volcanic rocks cool, magnetic minerals inside them can align with the surrounding geomagnetic field and become locked into that orientation. Sediments can preserve related information as well. By studying this paleomagnetic record, geologists have reconstructed a long history of polarity changes extending through millions of years. The reversals are irregular rather than occurring on a strict schedule. Sometimes hundreds of thousands of years pass between them. At other times, the intervals are much longer or shorter. This changing magnetic field also shapes Earth's interaction with space. The region dominated by Earth's magnetic influence is called the magnetosphere. The Sun constantly releases a stream of charged particles known as the solar wind. When these particles encounter Earth's magnetic environment, their trajectories can be deflected, guided, and trapped. The magnetosphere is compressed on the side facing the Sun and stretched into a long magnetotail on the night side. Charged particles moving through this environment can eventually contribute to auroras when they are guided into the upper atmosphere near the polar regions and collide with atmospheric atoms and molecules. Earth's magnetic field therefore provides important protection from some charged particles in the solar wind and helps shape the radiation environment around the planet. But it is worth keeping that role in perspective. The atmosphere is the primary shield protecting life at the surface from much of the harmful electromagnetic radiation and many high-energy particles arriving from space. The magnetosphere is an important part of Earth's protective environment, but it is not a single invisible force field standing alone between life and everything dangerous beyond the atmosphere. Perhaps the most revealing feature of Earth's magnetism is how different its origin is from that of a permanent magnet. A bar magnet relies heavily on electron spin, exchange interactions, magnetic domains, and crystal structure. Earth's global field is generated mainly by large-scale currents flowing through moving liquid metal in the outer core. The microscopic organization is completely different. Yet both produce magnetic fields, because the same electromagnetic laws apply. Moving electric charge generates magnetism whether those charges are flowing through a laboratory coil, circulating through liquid iron thousands of kilometers beneath our feet, or moving through plasma elsewhere in the universe. A compass needle quietly turning on a desk is therefore responding to currents hidden deep inside an entire planet. And beneath that planetary scale phenomenon lies the same fundamental connection between electric charge, motion, and the electromagnetic field. Once magnetism is no longer tied in our minds to bar magnets and pieces of iron, it becomes much easier to see how widespread it really is. Across the universe, magnetic fields appear wherever electrically charged matter is moving, and in space, there is a great deal of electrically charged matter. Stars, stellar winds, nebulae, accretion flows, and much of the thin material between stars exist partly or almost entirely as plasma. A plasma is a gas in which enough atoms have been ionized that electrons and positively charged ions can move separately. Because those particles carry electric charge, plasma conducts electricity. And wherever electric charges move, electric currents can arise. Those currents generate magnetic fields. The result is that some of the largest and most energetic environments in the universe are shaped by magnetism, even though they contain nothing resembling a conventional permanent magnet. Our own Sun provides a nearby example. The Sun is an enormous sphere of hot plasma, and its magnetic field is far more complicated than Earth's relatively simple large-scale dipole. charged material inside the Sun is constantly moving. The Sun also rotates differentially, meaning different latitudes rotate at different rates. Near the equator, the solar surface completes a rotation more quickly than regions closer to the poles. Combined with convection and the motion of conducting plasma, this helps generate and continually reshape the Sun's magnetic field through a solar dynamo. The magnetic field is responsible for many of the most dramatic features visible on and above the solar surface. Sunspots are darker regions associated with especially strong magnetic fields. Their magnetic structure suppresses some of the convective transport of heat from below, leaving the visible surface there cooler than its surroundings. Large arches of glowing plasma known as coronal loops trace magnetic structures extending high into the solar atmosphere. Prominences can suspend vast quantities of plasma along magnetic field configurations, and during solar flares, enormous amounts of stored magnetic energy can be released in relatively short periods of time. The Sun's activity also rises and falls in a cycle lasting roughly 11 years. The number of sunspots generally increases towards solar maximum and decreases towards solar minimum. Over approximately 22 years, the Sun's global magnetic polarity goes through a full cycle and returns to its original orientation. One of the most important processes behind sudden releases of magnetic energy is called magnetic reconnection. Magnetic fields in a plasma can become stretched, twisted, and forced into complicated configurations. Under appropriate conditions, the magnetic topology can rapidly reorganize. During reconnection, stored magnetic energy is converted into other forms, including heat and the kinetic energy of charged particles. Particles can be accelerated to very high energies, while plasma may be heated to millions of degrees. Magnetic reconnection occurs not only around the Sun but throughout space, including within Earth's magnetosphere and many astrophysical plasmas. Describing such environments requires treating the conducting fluid and the magnetic field as parts of one coupled system. The framework commonly used is called magnetohydrodynamics. Magnetohydrodynamics combines ideas from fluid dynamics with electromagnetism. Instead of tracking every individual electron and ion, physicists often describe the plasma as a conducting fluid whose motion affects magnetic fields, while those magnetic fields, in turn, exert forces on the plasma. This mutual influence can produce waves, instabilities, jets, turbulence, and remarkably complex structures. The basic principle behind stellar magnetism is therefore closely related to the geodynamo operating inside Earth. Conducting material moves. Electric currents arise. Magnetic fields are generated. Those fields influence the motion of the conducting material, creating feedback that can sustain a dynamo. The details vary enormously between planets and stars because their interiors, temperatures, rotation rates, and compositions differ, but the underlying electromagnetic principles remain the same. At the extreme end of cosmic magnetism are neutron stars. A neutron star is the compact remnant left behind after certain massive stars undergo core collapse. Although roughly comparable in size to a city, a neutron star can contain more mass than the Sun. Many neutron stars possess extraordinarily strong magnetic fields, and a special class known as magnetars takes this to an almost difficult to imagine extreme. Magnetar surface fields are thought to reach roughly billions to tens of billions of Tesla in the most extreme cases. A strong laboratory permanent magnet may produce a field around 1 Tesla. Earth's surface field is measured in tens of microtesla. The magnetic environment close to a magnetar is therefore not merely stronger by a modest factor. It exceeds familiar terrestrial fields by many orders of magnitude. Under such conditions, magnetic fields can influence the structure of atoms and the behaviour of matter in ways that would never occur naturally on Earth's surface. Even when cosmic magnetic fields are far weaker, astronomers can often detect them indirectly. One useful clue comes from synchrotron radiation. When electrically charged particles travelling at relativistic speeds move through magnetic fields, the magnetic force continually bends their trajectories. Because accelerated charged particles emit electromagnetic radiation, this curved motion produces synchrotron radiation. The radiation has distinctive properties including characteristic polarization. By observing synchrotron emission from astronomical objects, researchers can infer the presence and structure of magnetic fields that would otherwise be invisible. Radio telescopes have revealed synchrotron radiation from supernova remnants, jets launched near compact objects, entire galaxies, and vast regions within clusters of galaxies. Magnetic fields also thread the thin gas between stars. They influence how interstellar clouds evolve, how charged cosmic rays move through galaxies, and potentially how some regions of gas collapse during star formation. Our Milky Way possesses magnetic structure extending over enormous distances, with fields typically far weaker than Earth's field, but spread across regions measured in thousands of light years. Evidence suggests that magnetic fields also exist between and around galaxies and throughout galaxy clusters. Exactly where the earliest cosmic magnetic fields came from remains an active question. Small seed fields may have arisen through processes in the early universe or during the formation of the first cosmic structures. Later dynamos and turbulent motions could then have amplified and reorganized them. The precise balance between these possibilities is still being investigated. What is already clear is that magnetism is not a local curiosity belonging only to particular metals. It appears inside planets. It shapes the surfaces and atmospheres of stars. It helps drive solar eruptions. It influences interstellar plasma. It surrounds neutron stars with some of the most intense fields known in nature. And it can stretch across entire galaxies. None of those environments requires a permanent magnet in the everyday sense. They require electrically charged matter, motion, and the electromagnetic field. The same relationship discovered in a current-carrying wire operates across cosmic distances. Where charges move, currents can form. Where currents and electromagnetic fields evolve, magnetic structures can emerge. And from a compass needle on Earth to the violent magnetic field of a magnetar, all of it belongs to the same underlying electromagnetic physics. Take an ordinary bar magnet and cut it cleanly in half, and something slightly frustrating happens. You do not end up with one piece containing only a north magnetic pole and another containing only a south magnetic pole. Instead, you get two smaller magnets. Each one has its own north pole and its own south pole. Cut those pieces again, and the same thing happens. As far as every confirmed experiment with ordinary magnets is concerned, magnetic poles always appear together. This makes magnetism subtly different from electricity. An electrically charged particle can exist with a single sign of charge. An electron carries negative electric charge without needing a positive charge permanently attached to it. A proton carries positive electric charge. Electric field lines can therefore begin on positive charges and end on negative ones. Magnetic fields behave differently. The magnetic field lines drawn around a bar magnet form continuous loops. Outside the magnet, they are conventionally shown emerging from the North Pole and curving around toward the south. Inside the material, the field completes the loop. There is no confirmed point where a magnetic field line simply begins or ends because an isolated fundamental magnetic charge is sitting there. This is reflected in James Clerk Maxwell's classical equations of electromagnetism. Electric charge acts as a source of electric field. No corresponding fundamental magnetic charge has ever been observed, but physicists have spent more than a century wondering whether that asymmetry might be hiding something. A hypothetical particle carrying an isolated magnetic pole is called a magnetic monopole. Instead of always having a north and south pole together, a fundamental monopole would carry magnetic charge of just one type. A north magnetic monopole could exist on its own, with a south monopole potentially existing somewhere else entirely. No such fundamental particle has yet been confirmed, but there is a remarkably good theoretical reason physicists have continued looking. In 1931, Paul Adrian Maurice Dirac investigated what would happen if magnetic monopolies existed within quantum mechanics. He discovered a beautiful connection. The existence of even a single magnetic monopole anywhere in the universe could provide an explanation for why electric charge appears in discrete units. Electric charge is quantist. Every freely observed electric charge comes in amounts related to a fundamental unit rather than taking completely arbitrary values. The electron, for example, always carries the same magnitude of charge. Dirac showed that if a magnetic monopole existed, consistency between quantum mechanics and electromagnetism would require electric and magnetic charges to obey a quantization condition. In other words, the existence of magnetic monopolies could help explain one of the most fundamental features of electric charge. That did not prove monopolies exist, but it made them considerably harder to dismiss as mathematical curiosities. Later theories gave physicists additional reasons to take the possibility seriously. Some grand unified theories developed during the 20th century predict magnetic monopolies as natural consequences of the way fundamental forces may have behaved at extremely high energies in the early universe. Theoretical work by Gerard 't Hooft and Alexander Polyakov showed that monopoly solutions can emerge in certain gauge theories without simply being inserted by hand. If such objects were produced in the very early universe, some might conceivably have survived until today. That possibility has inspired many searches. Researchers have looked for monopolies in cosmic rays, geological materials, meteorites, particle detectors, and accelerator experiments. At the European Organisation for Nuclear Research, experiments associated with the Large Hadron Collider have searched for unusual highly ionizing particles that could be signatures of magnetic monopolies. Specialized detectors have been designed partly because a monopole, if it exists with the properties predicted by some theories, could interact with matter very differently from an ordinary electrically charged particle. So far, however, no fundamental magnetic monopole has been experimentally confirmed. That statement requires one important qualification. Physicists have created systems in condensed matter that contain excitations behaving in some respects like magnetic monopolies. One famous example occurs in materials known as spin ice. The microscopic magnetic moments in these materials occupy geometrically frustrated arrangements, meaning they cannot all simultaneously settle into the simplest preferred configuration. Certain disturbances in this magnetic ordering can behave as though separated north and south magnetic charges are moving independently through the material. These are sometimes called emergent magnetic monopolies. They are real physical quasiparticles within the material, and their behaviour is scientifically fascinating. But they are not the same thing as a fundamental magnetic monopole existing freely in empty space. They emerge from the collective behaviour of many underlying magnetic moments, rather like other quasiparticles that appear inside solids. The distinction matters. Discovering a monopole like excitation inside spin ice does not mean someone has finally found the elementary magnetic counterpart of an electron. For now, the fundamental asymmetry remains. Nature contains isolated positive and negative electric charges. Yet every confirmed fundamental source of magnetism behaves without isolated magnetic charge. That is one reason the familiar equations of electricity and magnetism are not perfectly symmetrical, despite the deep unity of the electromagnetic field. If genuine magnetic charges existed, the equations could be written in an even more strikingly balanced form. Perhaps they do exist somewhere and are simply extraordinarily rare or difficult to produce. Perhaps they were created in the early universe and diluted to almost undetectable concentrations. Or perhaps fundamental magnetic monopolies do not exist at all. Experiment has not yet settled the question. What it has settled, at least for everyday magnetism, is equally important. The north and south poles of an ordinary magnet are not piles of separate magnetic particles gathered at opposite ends. There are no known microscopic north charges hiding at one end of a bar magnet and south charges hiding at the other. Instead, the magnetism comes from electrically charged quantum matter. Electron spin and orbital behaviour provide magnetic moments. Quantum interactions allow those moments to organise collectively. Magnetic domains determine how that organisation appears across the material. And the resulting configuration creates a magnetic field extending into the surrounding space. So when two magnets pull together, their poles are very real features of the magnetic field. But they are not known to be elementary magnetic charges. Break the magnet apart, and the underlying field reorganizes into new north and south pairs. No matter how many times we divide the ordinary magnet, the elusive isolated pole refuses to appear. And somewhere between that simple kitchen table experiment and the deepest theories of particle physics lies one of magnetism's oldest unanswered questions, whether nature has hidden a truly solitary magnetic pole somewhere in the universe. So what is magnetism actually made of? The most precise answer is that magnetism is not made from a separate magnetic substance at all. It is a manifestation of the electromagnetic field, shaped by electric charge, motion, and the quantum properties of matter. That answer is much less mechanical than saying a magnet contains some hidden material that flows outward from its poles. But it is also much deeper. At the classical level, the story begins with electric charge. A stationary charge produces an electric field. When electric charges move, as they do in an electric current, magnetic fields can appear around that motion. James Clerk Maxwell's theory of electromagnetism brought these ideas together. Electric currents create magnetic fields, changing magnetic fields create electric fields, and changing electric fields can themselves contribute to magnetic fields. Electricity and magnetism are therefore parts of one connected system. Albert Einstein's special theory of relativity made that unity even clearer. An electric field and a magnetic field are not two entirely separate ingredients placed side by side in nature. They are different aspects of a single electromagnetic field. Observers moving relative to one another can divide that field into electric and magnetic components differently. A situation that one observer describes as involving both electric and magnetic effects may be described by another observer with a different balance between them. The underlying electromagnetic field remains the same, so magnetism is already deeply connected to electricity and motion before quantum mechanics enters the picture. But permanent magnets require something more. Inside matter, electrons possess electric charge. Their quantum states can also carry orbital angular momentum, and because charged particles with angular momentum have magnetic properties, this can contribute an orbital magnetic moment. Electrons also possess intrinsic spin. Spin is not literal rotation of a tiny electron around its own surface. It is a fundamental form of quantum angular momentum built into the electron itself, and spin gives the electron an intrinsic magnetic moment. That means a single electron already carries one of the microscopic ingredients required for magnetism. But individual magnetic electrons are still not enough to explain a strong permanent magnet. Most materials contain enormous numbers of electrons, and yet show almost no permanent magnetic field. Their magnetic moments may pair, cancel, or remain oriented in different directions. Strong magnetism appears only when matter allows those microscopic moments to become organized. In ferromagnetic materials such as iron, quantum mechanical exchange interactions can make particular arrangements of neighboring electron spins energetically favorable. The exchange interaction is not a mysterious extra force. It emerges from electromagnetic interactions combined with quantum mechanics, the Pauli exclusion principle, and the rules obeyed by identical electrons. Under the right conditions, these interactions allow large populations of magnetic moments to develop collective order. Even then, a useful permanent magnet requires additional structure. Ferromagnetic materials divide into magnetic domains. Within each domain, many magnetic moments share a common orientation, while different domains can initially point in different directions. An applied magnetic field can rearrange these domains. Magnetic anisotropy created by the crystal structure can favor particular directions. Hysteresis allows the material to retain part of its magnetic organization after the external field disappears. High coercivity makes that organization difficult to reverse. Together, these effects transform microscopic quantum magnetism into a macroscopic object capable of remaining magnetized for years. But there is a still deeper description. Quantum electrodynamics describes electrically charged particles interacting with the quantist electromagnetic field. In this theory, the electromagnetic field is fundamental, and photons are its quantist excitations. This does not mean that a permanent magnet is continuously spraying invisible photons into the room. A static magnetic field is better understood as a particular configuration of the electromagnetic quantum field. Real photons are propagating excitations of that field, such as the photons making up light. The language of photon exchange can also appear in calculations of electromagnetic interactions, but it should not be turned into the literal picture of tiny pellets constantly flying back and forth between stationary magnets. Modern particle physics goes deeper still through the idea of gauge symmetry. Gauge symmetry is a principle describing how certain changes in the mathematical representation of a field can leave observable physics unchanged. Electromagnetism is described by a gauge field, and the photon is the quantum associated with that field. This gauge structure is not merely an elegant mathematical decoration. It helps determine the form of the electromagnetic interaction itself. Within the standard model of particle physics, electromagnetism is also connected to the weak nuclear interaction through electroweak theory. The work of Sheldon Lee Glashow, Abdus Salam, and Steven Weinberg helped establish this deeper framework. At very high energies, the electromagnetic and weak interactions are described as different manifestations of an electroweak structure. As the early universe cooled and electroweak symmetry was broken, the familiar photon emerged as a massless quantum associated with electromagnetism, while the carriers of the weak interaction became massive. So there is a hierarchy to the explanation. A magnetic force appears because something is interacting with a magnetic field. That magnetic field is one aspect of the electromagnetic field. Electric charge, electric current, and changing electromagnetic fields determine how that field is sourced and evolves. Inside atoms, electron orbital states and intrinsic spin create microscopic magnetic moments. Inside magnetic materials, quantum exchange interactions can organize those moments. Domains, anisotropy, hysteresis, and coercivity can then preserve that organization strongly enough to create a permanent magnet. And beneath all of it, quantum electrodynamics describes charged quantum fields interacting with the electromagnetic quantum field. That is as far as experimentally established physics currently takes the question. We can describe electromagnetism with extraordinary precision. We can calculate the magnetic moment of an electron to astonishing accuracy. We can predict how fields evolve, how photons interact with charged particles, and why different materials respond to magnetism in dramatically different ways. But eventually, any question asking what something is made of reaches a boundary. Why does nature contain an electromagnetic field at all? Why does that field possess the particular gauge symmetry it does? Why does the electron carry exactly the charge and quantum properties that it does? Current physics can describe these facts and connect them within powerful theories, but it does not provide a final answer to why reality has chosen this particular underlying structure. So a magnet is not hiding a supply of magnetic material inside itself. Its invisible force is the large-scale expression of something far more fundamental. Electric charge, relativity, quantum spin, collective electron behaviour, and the electromagnetic quantum field all contribute to the simple push or pull we can feel between two magnets. What seems like one ordinary force is really an entire hierarchy of physics, reaching from a piece of metal in your hand all the way down to one of the fundamental fields woven through the universe. So, what is magnetism actually made of? Not a hidden magnetic substance, and not microscopic north and south particles packed inside a magnet. Known magnetism is an expression of the electromagnetic field, shaped by electric charge, motion, and the quantum properties of matter. Hans Christian Ørsted showed that electric current can generate a magnetic field. Michael Faraday then demonstrated the reverse connection, while James Clerk Maxwell united electricity and magnetism into a single theory of the electromagnetic field. Albert Einstein took that unity even further. Special relativity showed that electric and magnetic fields are not fundamentally separate entities, but interconnected aspects of the same electromagnetic field, described differently by observers in different states of motion. Inside matter, the story becomes quantum mechanical. Electrons can contribute magnetic moments through orbital angular momentum, but they also possess intrinsic spin. That spin is not a tiny electron physically rotating like a miniature planet. It is a fundamental quantum property. Otto Stern and Walther Gerlach revealed the quantist nature of angular momentum experimentally, while George Eugene Uhlenbeck and Samuel Abraham Goudsmit later introduced electron spin as an intrinsic property. In strongly magnetic materials, these tiny moments can begin acting collectively. Werner Karl Heisenberg helped explain how the quantum mechanical exchange interaction can favour organised spin arrangements, producing ferromagnetism. Magnetic domains then organise this alignment across larger regions. Hysteresis allows some magnetisation to remain after an external field disappears. Coercivity resists reversal, while magnetocrystalline anisotropy makes particular magnetic directions energetically favourable. Together, these effects turn microscopic quantum magnetism into a stable permanent magnet. But permanent magnets are only one way of producing magnetic fields. Earth generates its field through the geodynamo, driven by moving electrically conducting fluid in its outer core. The Sun produces magnetic fields through the motion of plasma, and similar electromagnetic processes operate throughout stars, galaxies, and other cosmic environments. At the deepest experimentally established level, quantum electrodynamics describes charged particles interacting with the quantum electromagnetic field. Photons are quanta of that field, but a stationary magnet should not be imagined as continuously spraying photons into space. Its magnetic field is a persistent configuration of the electromagnetic field itself. So the clearest answer is this. Magnetism is an expression of the electromagnetic field, sourced and shaped by electric charge, motion, intrinsic quantum magnetic moments, and the interactions between them. And that means a small magnet held between two fingers is far more extraordinary than it appears. Inside that quiet piece of material are special relativity, quantum mechanics, quantum field theory, and unimaginable numbers of electrons collectively organizing their magnetic behavior. Something simple enough to stick a note to a refrigerator is, underneath, an everyday expression of some of the deepest physics we know.